Okay, once again, we're going to work this out for weight of 0.3 newtons and angle of elevation 17 degrees with coefficient of moving friction, kinetic friction. This is actually rolling friction, but we're not going to make a distinction, 0.02, 2%. So the Wx is going to be W times the cosine of 270 minus alpha, and I'm going to use this particular version of the angle. So it's going to be magnitude of W being 3 newtons. It's going to be 0.3 newtons. 0.3 newtons times the cosine of 253 degrees times the I vector. It's going to be our Wx vector. The cosine of 253 degrees is about negative 0.27, give or take a tenth. That's my mental estimate. You can check that out. And if we multiply this out, we get approximately 0.08 newtons, actually be 0.081 if we use the 0.27. And we're being a little loose with significant figures here. I'm not really following it carefully. When we get down to the calculation of friction, we go to another significant figure, but we're eliminating a significant figure up here. So this is not, this calculation is for illustration, and we're not really respecting the significant figures. You should be aware of that. Okay, the Wy is going to be 0.3 newtons times the sine of 253 degrees, 253 degrees being the angle from here around to here, 270 minus our 17, and that gives us negative 0.29 newtons times J. And I think that one you can kind of take to the bank. I'm pretty sure that one's right. But in any case, by all means, verify my calculation there. And of course, you can do these calculations to a greater number of significant figures. They won't really correspond to anything that we could do with a Hot Wheels car and a weight over a pulley. We don't have that much precision, I don't think. We'll investigate that hands-on in the lab, perhaps. Okay, the normal force is going to be negative the Wy force. That's going to be plus 25 newtons times J. So we see the negative 0.08 newtons times I. That's going to be your Wx. We see the Wy, which is between 3 and 4 times as great as the Wx, but in the J direction. And that corresponds fairly well to the picture. The normal force being equal and opposite to the Wy, 0.29J being this vector, and the frictional force 0.006 newtons, actually less than 1/10 of this. That doesn't correspond very well with the picture. This vector is a lot bigger compared to Wx than what you would get with these conditions. In any case, we get these vectors, and the F friction doesn't have an arrow over it. I don't have a direction on it. I just have F friction with no arrow, which means this is the magnitude of the frictional force. We have to put a direction on the frictional force, and that direction is going to depend on whether the cart is moving up the incline or down the incline. If it's moving up the incline, then the incline being in this direction, the net force, well, the frictional force is going to be down the incline, unlike the way I've drawn it here. So you're going to have a frictional force of negative 0.006 newtons times I, and that reinforces the negative 0.08 newtons times I that we have here, giving us a net force of 0.086 newtons times I. Whereas if the cart happens to be moving, or the car happens to be moving down the incline this way, then this picture has all the right directions. The force of friction will be in the positive x direction. The x component of the weight, the component parallel to the incline, will be in the negative x direction. And we're going to get, I haven't written out all the details, but it'll be negative 0.08 newtons times I plus the 0.006 newtons times I. Again, because the frictional force is now in the positive x direction. And when we add that up, we get negative 0.074 newtons times I.